and we can talk. So in the previous episode, in episode 62, if you guys checked it out, with Dr. Pekka Sinervo, he spoke about something quite interesting, a very interesting idea that Newton actually originally thought of as well. Like, this was his original interpretation of force and acceleration, that force wasn't really an actual measurable quantity. It was simply a theoretical concept. What was measurable is the acceleration. We look at a body, we watch it accelerate, and we say there's a force. Even if someone like hits us like a force, what we're really feeling is our body moving. And via that motion, basically that acceleration, we are interpreting that there was a force applied. So that is a big thing that, the second law gets out. Just that relationship between both of these variables.
Mm-hmm. And also, a lot of people refer to the second law as F equals ma, but there's actually another way to look at this law. And
let's see it.
You do need like a little bit of calculus notation here, but I'll try to be very explicative. So the velocity is the rate of change of the position with respect to time. So we're going to say it's dx by dt, right? That's just notation, okay?
Yep.
And then acceleration is the rate of change of velocity with respect to time. So it's dv by dt, but also since v is dx dt, then we could say it's the second derivative of position with respect to time. Now, momentum is defined, it's just a quantity defined by the mass times the velocity. And so as we talked about a little bit earlier, if there's a big box, very heavy, moving towards you at a slow velocity, right, it's going to be hard to stop that box. But it will be equally as hard to stop a light box moving at a fast velocity, because the momentum is proportional to the mass and velocity. So if you tone down the mass, increase the velocity, you can have the same amount of momentum coming at you from two different types of boxes, right? So the force is actually defined as the rate of change of the momentum with respect to time. And this actually relates to the rocket science episode that we did, because notice how the rate of change of momentum is the rate of change of mass times velocity. And so not only can this, like, if your mass is constant and you know that for sure, then that just becomes mass times acceleration, because you can pull that out of the derivative.
Well, not
But
acceleration, just change in v. Oh, because you're saying force equals force. Yeah.
So yeah, force is going to be mass times acceleration.
Yeah.
But like we talked about in the rocket science episode, if you have an object that has a variable mass and a variable velocity, then it's not so simple, because now all of a sudden, for my calculus students out there, you have a product rule because now your mass is a function of, it may be time or position, and your velocity is also a function of time or position. And so you have to do some product rule, chain rule business, and your equation for force is going to be very more complicated, whatever the
more
word.
Complicated for sure.
Yeah,
it's going to include all of these important terms, but the idea behind that again is that momentum term, right? Like understanding that change in momentum relationship with force. So now we can not only understand the relationship between acceleration and force, but now we also have another relationship to go by, the force and the change in momentum, which is an interesting thing. Have we even have we spoken about momentum? I don't think we really touched on it too much. But like, again, I mean, we were kind of discussing it this whole time. Basically, like, your mass times velocity, and again, that's more translational momentum, and we can also kind of
and one awesome thing about momentum is the conservation
Oh,
momentum.
that's a big one.
But I guess I think we could save this for another episode where we talk about energy and momentum together. That would be good. Anyways, we can talk. We can keep talking about.
I think conservation of momentum is quite important in this kind of regard, and it wouldn't take too long because it's just saying that. I think it's an important concept because momentum, like energy, is an important concept by itself, and we can make an episode on that. But I don't think we should sacrifice what we can talk about here.
Well, go right ahead.
You know what I mean? So momentum, as we were talking about, very, very important concept, relating, as you were saying, like, the amount, like how hard is it to stop an object or to move an object. It's dependent both on its mass and velocity. So here, the conservation of momentum law is kind of a universal law, which is basically for any isolated system, no matter what happens, no matter what interactions are occurring, the total momentum of that system will always be the same, no matter what. And what does this entail? Well, think about a very simple example, and this is usually what people start with, a billiard ball, playing pool, for example. Like when you hit a ball and it hits another one, I mean, in a perfect world, obviously we don't live in a perfect world. Like there's still edges on the ball and stuff like that. But in a perfect world, that ball would transfer all of its momentum to the other one, or the ball would hit the other one and they would both take some portion of the momentum. Or, the ball would just rebound and take all the momentum. Basically saying that the momentum of those two balls, the total momentum of those two balls, will always be the same. So in an isolated system. Kind of the gist of the conservation of momentum. Very important idea. Also, I believe, thought of from Newton's laws of motion. Right.